Good morning, Astronomy 1010. Welcome to Lecture 4, Part 1 and Lab 4. Before we begin, I'd like to say a word about today's lab. Daniel asked me which pages we're going to need. In today's lab, we're going to be making a model of an ellipse, and I provided a number of different materials depending on what your skill or resource level is. So let's go over here to Lab 4. If I could have things my way, I thought I also had a printout of an ellipse. If I could have things, If I could have things my way, the page that we want to print out is this one here. So if we're using the PDF, it's page 5, which is 5-5. I'm actually going to hit print on it now. Just page 5. Okay. And so this is the page that we're going to make our ellipse model on. But this lab actually might require a few materials. Let's go to speaker view and me. Ideally, if you could find these things kicking around your apartment, it would be a piece of cardboard, a nice thick piece of cardboard like you might find on an industrial wine box, a loop of string cut to 32 centimeters and then tied so that in a loop it's about 15 centimeters long, and then just 2 push pins or maybe thumbtacks if you've got nothing better. And that plus a ruler, we're going to make ourselves a beautiful model of a planetary orbit, which you will learn today takes the form of an ellipse. So those of you who cannot rustle up these materials, if you don't have a printer, you'll have to make this page by hand, which shouldn't be too tough. I think these things are about 12 centimeters apart, and you'll have to put in these lines at the bottom and then a thing at the top for your name. I could also give you a copy of my ellipse that I scanned for you to work from. I've learned that some people can't handle this thing. They either can't find the push pins or the thumbtacks and the string. They just can't handle the going around in a circle with a pencil. They're not crafty. If we were in lab together, I would force you to do it because I would have the materials there and there would be no excuse. But I'm not trying to make allowances for the fact that you might not have all the resources you need at your house. So I also have a model of an ellipse that I drew that you could work from. That's way less cool. So if you're uncool, use that. If you're cool, do it right with me, okay? Now, just give me 1 second here. Sorry, Daniel, if you can do me a favor, I noticed in Blackboard here that the ellipse is not up. This is the PDF version. I don't know exactly why. I'm sorry, the docx version. Not sure why I did that, but I do have a copy of the ellipse. I guess I could do it now. I hate to waste the time, especially because my computer is acting slow.
If you can do it during the break, that would be fun. Yeah.
I guess I'm just worried that here I have sort of a planet ellipse drawing JPEG. All right. So remind me that I should do this for the other sections as well. That's section 1. I don't know, maybe section 2 has it.
I don't. I know section 2 does not, but you can, but it's probably easier to do it during the break so that way we can get straight to lecture.
Yeah, you're right. You're so right. And that's why I'm totally listening to you right now. Here we go. Okay. Sorry, I've got a bit of compulsive behavior and you're seeing it in action. All right, I'll get the last one during break. Remind me to do it for the nighttime class during break. Okay. Today we're going to continue on with our history lesson, and we're going to learn about the Copernican Revolution. And the Copernican Revolution came, almost like 1,000 years. Well, it depends if you measure it from Aristotle or from Ptolemy. But it came much later, after the Greek geocentric model of the solar system was created. You will remember that the Greek geocentric model found its highest expression in the form of Ptolemy's Almagest, slide 47. Ptolemy, the Arabic Greek mathematician, had mastered the geocentric model by adding over 100 rotating epicycles to describe the orbits of sun, moon, 5 planets, and stars. And his book, The Almagest, was used as the sort of standard text in astronomy to describe the motions of the planets. Over the next 1,000 years or so, the model started to break down because it did not actually philosophically represent the true nature of planetary orbits. Planets do not actually orbit Earth, they orbit the sun. And the small inconsistencies grew to larger ones, where I'm hearing some crazy echo here, so someone needs to mute themselves. All right. And these inconsistencies led people to doubt the veracity of the Ptolemaic model. Other problems were that the computation of planetary orbits required a lot of time, specialized knowledge in mathematics, and very few people could actually perform these sorts of calculations because the number of, the number of people who could do this sort of work were few in number, and they would represent some kind of priestly class that were mathematicians within the Holy Roman Church. After sort of the Middle Ages, during the Middle Ages, astronomy was mostly preserved by Arabic astronomers. The Crusades had brought an influx of knowledge from the ancient world into Europe. And this would be sort of the start of the Renaissance. Thousands of years later, more than 1,000 years later, Nicholas Copernicus was inspired by the works of the ancient Greek philosophers. But ironically, his decision to place the sun at the center of the solar system was a desire to make it more Platonic and less Ptolemaic. Plato, you remember, believed that the orbits of planets should have simple circular motion, and that circles were these sort of ideal harmonistic geometry shapes that kept the universe from becoming unwound. By placing the sun in the center of the solar system, Copernicus realized that he could reduce the number of epicycles and make the solar system this more circular orbit sort of paradise that Plato had imagined. So let's take a couple of notes about the Copernican Revolution, the heliocentric revolution. And this is where we get our modern heliocentric theory of our solar system. My marker's getting a bit weak here, so this one's in good. So Nicholas Copernicus, working in the 1500s AD, was a Polish astronomer, mathematician, and it's worth mentioning, a cleric in the Holy Roman Church. I think this was before Protestantism. So the Holy Roman Church, at the time of Nicholas Copernicus's dabblings, was the dominant political institution all throughout Europe. It was not just a religion, it was also a government, right? And he was a functionary in that government who probably performed mathematical calculations and God knows what else. And his big idea was to place the sun at the center of the solar system. Copernicus sort of invented heliocentrism. Well, I suppose you could also give the credit to the Greek Aristarchus, who came up with this idea during the period in which Aristotle was working. But we credit Copernicus with making a first heliocentric working model of the solar system, and it actually taking hold and catching on. He, as far as we know, he did not know about the writings of Aristarchus, or if he did, we didn't find any books that or any reference to it in his works. So the placing the sun at the center of the solar system had two advantages. One, it gave the planets simple circular motion. Now, it ended up being needed a few epicycles to make the thing work, but nowhere near as many as Ptolemy did. The more important thing was that Copernicus now had a new description of retrograde motion. Okay, which one of my students can remind the class about retrograde motion so I know that I'm talking to an enlightened audience here? I'd really appreciate someone telling me what retrograde motion is in simple words. Or
All right. Well, since nobody else is stepping up, so I don't know how well the camera would work from mine, but normally the rotation would be, if this is east and this is west, it would be normally it would be going this way, but there's a period where it actually slightly goes backwards and before moving onwards.
yeah, that's not a bad quick and dirty explanation, Daniel. It's a temporary westward motion, and it usually takes the form of a loop in which a planet temporarily shifts backwards or westward along the ecliptic, right? And Greeks used epicycles to sort of account for this seemingly non-circular motion that that resulted from time to time with the planets. By placing the sun in the center of the solar system, Copernicus had discovered the true reason for retrograde motion. It was simply an artifact of what we last time called parallax. It's a geometrical illusion caused by Earth going past the planets in its orbit. Now, let's remind ourselves that this would be the ecliptic, and this would be east, and this would be west. You'll notice that the planets are traveling east or counterclockwise around the sun. In configurations 1, 2, and 3, both Mars and Earth travel eastward along the ecliptic, but Earth is closer to the sun and it moves faster around the sun, so it starts to catch up to Mars, but it keeps seeing Mars from a vantage point where Mars is sort of, I don't know how to put this, but to the left of Earth, and that makes it appear to be shifting eastward along the ecliptic. However, when Earth passes Mars in configurations 4 and then 5 and 6, as it travels past Mars and gets ahead of it, Mars now appears to the right and appears to temporarily be shifting backwards or westward relative to the constellations in the ecliptic. And this persists for a little while. And then, I don't know, after a month or so, maybe a few months, then it starts to appear to drift eastward again as Earth gets farther away from Mars. Now, when we talked about Aristotle last time, we referred to another similar shifting of a near ground object relative to a background one, or an angular shift in the displacement of stars, and we referred to that as parallax. This is another version of parallax. It's when objects lie at different distances and you move with respect to them, you can sort of see them shifting complicated ways. This description of retrograde motion was nice because it follows a principle in philosophy called Occam's razor. When two competing explanations of an observation are given, and neither one has, you've got no right, both of them equally describe the observations, the explanation that is the simpler one is to be preferred. And Copernicus's description of retrograde motion was simpler because it involved fewer epicycles. However, there was a problem with the Copernican model. And the problem was this: Copernicus is still using perfectly circular orbits because he was also influenced by Plato, just like Aristotle and Ptolemy. And circular orbits are not the correct description of planetary motion. Because of this, this led to errors in the model describing observations. And I don't know all the gory details, but I understand the principle. The principle would say, okay, Mars should go into opposition on January 29th, but instead it goes into opposition on January 31st or something like that. Things weren't aligning with the dates they were supposed to, and the positions of the planets that the model described did not match the positions once they were in orbit.
Alan's not in this class.
Say that, Devin?
Alan's not in our class.
So I don't understand. Who's Alan?
He just joined up.
Oh, well, I don't care. Let him sit in and learn something, right?
No, he doesn't pay to be here. No.
Well, when you pay, that's when you get a grade. In a way, you're paying so that you can take the test. But if Alan wants to learn some astronomy, doesn't bother me unless he's a
I
jerk.
think he's trying to fuck around. So
Oh, really? What's he doing? Is he doing something funny?
he is. Look at the recording.
I'm missing it, but I guess because I was talking. Well, we can give Devin, if it's troubling you, we can give him the boot, but I don't see him here. You keep an eye on things for me, Devin, okay? You watch out for that crazy Alan guy. We won't let him mess us up.
Oh, I hope so.
Okay. All right. So there are errors in the model describing observations. Thus, this led to some confusion, some debate. There was also another problem. And problem number 2 was what led to there being a debate about heliocentrism versus geocentrism that dominated the astronomical community for hundreds of years to come. And the problem number 2 was that there were thinkers in the Holy Roman Church, and these thinkers were St. Thomas Augustine, St. Thomas Aquinas, and the Holy Roman Church had used Aristotle.
Daddy?
What's going on there? Someone forgetting to mute themselves? What's going on with people today? Is there some craziness going on? Is Mercury in retrograde? What's happening here, right? We need to.
You wouldn't be the only one that has heard of that. I used to hear that in one of my previous jobs about how Mercury retrograde was when everything went crazy.
Yeah, people love that stuff, you know. They'll look for any explanation except for the true one, because that requires more work, you know, because then you have to sit down and concentrate, and people don't like that. Okay, the Holy Roman Church used Aristotle's logic. They used the logical arguments of Aristotle to attempt to prove the existence of God. And remember, Christianity comes after Roman theology and philosophy. And you'd be crazy to think that the Holy Roman Church wasn't influenced by Roman ideas. In fact, some ideas that are the deepest ideas of Christianity about heaven being this ideal, perfect place, that's a Platonic ideal. That actually comes from some pagans who worshiped faceless spheres rotating through the heavens, okay? That's not a Christian idea. That's a Greek Roman idea. And if you use Aristotle's syllogisms and logic to prove the existence of God, that means that Aristotle can't be wrong about the heavens, or he could be wrong about anything. In a way, using Aristotle to prove the existence of God has the awkward effect of backdoor deifying Aristotle. So to come out and to say that Aristotle was wrong when he argued for an Earth-centered universe would be deeply troubling to people of the Middle Ages or the Renaissance. Because he knew this, because Copernicus knew that this would be troubling. I lost you guys, I'm sorry, I'm clicking buttons here. Copernicus did not publish his theory of the solar system until he was lying in his deathbed, and he wrote a book called On the Revolution of the Heavenly Spheres, or De Revolutionibus, as it's called in Latin. And he wrote a foreword in this book saying, you know, I'm about to do something that's going to make people feel a little uncomfortable when I place the sun at the center of the solar system. And, you know, I'm a member of the team here, guys, and I know that's not cool, but here's a thought. Maybe it's just a mathematical model. Maybe we don't have to think about it as real reality. And think about it. I can describe retrograde motion pretty slick, right? By the way, I'm out of here, so good luck with this. And he published this book, and now a whole bunch of thinkers who understood science and mathematics had to start debating. Well, so this is the book, De Revolutionibus Orbium Celestium. And this is the work on the heliocentric theory published by Copernicus. I was hoping we might see a page or a folio from this book, but you know, we won't go into it too much. Like Ptolemy's Almagest, it also featured orbits of the planets and a description of how to make this mathematical model. Because he had a new description of retrograde motion, and because it was a novel idea, people were thinking about it. But the problems where the circular orbits led to errors in the description of observations gave people room to doubt that he actually knew the correct interpretation of the universe. And thus began a great debate in Europe all throughout the the Renaissance, heliocentrism versus heliocentrism. Heliocentrism versus geocentrism. Which model of the heavens was correct? After Nicholas Copernicus did this, other scientists came along who were impressed by this idea, and they began to take more careful observations to see if they could discriminate which of the two models was correct. And this is going to usher us into the era of modern science, where you have competing hypotheses of a problem in nature. Does Earth orbit the sun, or does the sun orbit Earth? And you try to resolve the debate through observations of the natural world. And the person who came after Copernicus, 100 years afterwards, who wanted to resolve this debate was one of the most legendary astronomers you've probably never heard about, a Danish astronomer named Tycho Brahe. Tycho Brahe was inspired as a young man when he used Ptolemy's Almagest to observe an eclipse in the 1500s, and the eclipse came on the date that Ptolemy predicted, but something like 20 minutes late. Supposedly this drove a young Tycho mad, that there was a man who lived 1,200 years before him who knew there would be an eclipse when he was alive, but that the eclipse would come just 20 minutes later than was expected. Okay, is that accidental or intentional? Now I've got to look for the non-video participants. Do I have to start putting like a waiting room in this class? That would be really lame. Okay. Is this Alan? Is that the guy you were talking about, Devin? He's gone. See you, Alan. You're out. I guess I should have checked to make sure he wasn't a student, but there's kind of a lot of you guys. It's hard to keep track of everyone. Whatever. All right. Let's take some notes on Tycho Brahe. Devin, is he a friend of yours or something? Is that what's going on, or what's going on? Can you give me any enlightenment onto this, or?
Sorry, what? I don't have my earpod in.
Never mind.
Okay.
Okay, some notes on Tycho Brahe. Tycho Brahe was a legendary Danish astronomer. He's considered by modern astronomers to be the greatest naked eye astronomer to ever sort of do science and astronomy. He worked just in an era before telescopes were discovered. So he's considered the greatest of the naked eye astronomers. And it's said that he mapped every star in the sky to a positional resolution of approximately 3 arc minutes. In other words, he knew the right ascension and the declination of every star in the sky to within 3 minutes of arc. That's considered impressive because this is the limit of what human vision will allow. He could not have done any better without a telescope, in other words. And the reason he did this, he also took careful observations of planetary positions especially Mars, which turned out to be crucial later on. Now, Tycho Brahe was a colorful fellow. He was a sort of a loudmouth braggadocio and a heavy drinker. And he used to start fights with people over who was the better mathematician. Supposedly, the legend goes he had his nose cut off in a duel with another gentleman over who's the better mathematician. Tycho lost and got his nose cut off. So they replaced it with gold. He had a golden nose. And the Danish king thought that Tycho was kind of a fun, crazy dude to party with. And so he decided to help Tycho Brahe on his quest to discover which model of the solar system was correct, heliocentrism or geocentrism. And he purchased for Tycho his own private observatory. He gave him his own island off the coast of Denmark called Uraniborg. And on Uraniborg, which, by the way, the island still exists, but now it's called something really boring like Sven or something. Okay, so it's something simple like that, but I think Uraniborg is pretty cool. And here's a little illustration of the great observatory built at Uraniborg, where Tycho Brahe could take his observations. Here's a woodcut showing the great astronomer Tycho in front of a device that's known as a mural quadrant. A mural quadrant is kind of like a giant sextant, which allows you to take angular measurements of stars. And you'll notice that up here, it got a little cropped off, but there's a slot cut into the wall pointing towards the observer's meridian. That's when a star makes its highest journey through the sky. And you can use the angular measurement device to carefully track the position of the star and measure its angular position. He brought some friends with him. He brought a German mathematician, his graduate student, who was Johannes Kepler. We'll learn about him in a moment. And there was also a dwarf who did some cooking and cleaning and record keepings. So out to Uraniborg go Tycho and his buddy Kepler and the dwarf, and they all begin this program of observations. Now, does anyone know why charting the angular positions of stars down to a resolution of 3 arc minutes would help solve the debate between geocentrism versus heliocentrism? And here's a hint, it's got something to do with Aristotle and the last lecture that we had. Why would it be so important to know the positions of stars? Oh, that's a cute kitty, Melissa. I forgot that cat's name.
Nala.
Nala. Have we seen Nala before? I can't. Yeah. I like that cat.
Don't the stars like tell stories of like back in the day?
Well, there is a mythology associated with constellations, but that's not what this is about. This is about something observational. It's about something you had to be here for last lecture.
I'd be bullshit. I'm starting to pay attention while my grades reflecting. So
All right, well, we like that. So does anyone have notes from the end of last class? Aristotle's argument for why Earth had to be stationary? It's all about that. I was
Preston C was supposed to help me out. It's my buddy, but he hasn't given me any notes.
Well, he doesn't have to help you out, Devin, because all of these lectures. I don't know what the hell's going on there, but we got to mute this person.
I just wanted to thank
Hold on a sec.
um,
Who the shit is
I
that?
just wanted to thank Preston C for sending me the link.
All right, Johnny Jillian. Do I know that? I can't tell who's in this class anymore. Hey, listen, guys. First of all, let me clear something up, Devin. You don't need anyone.
Preston C sent me the link.
Devin, you don't need anyone to help you catch up to,
You keep muting me.
because you're glitching out and you're broken up and you're interrupting me, and I don't even know who the hell you are because I've never seen you before. Are you in this class? I'm gonna figure this out. I guess I have to take some time to do that. Yeah, I don't
Well, if I
even know who this is. You're out. Get out of here. If you're not part of this class, then like you can't just come in and barge in. Like that's not cool. How do I remove you? Yes. Bye. Don't come back. And Devin, I don't know if you're giving these people the link, but I'm going to remove you too if you continue to disrupt. So I don't know if you're doing this intentionally or not, but I have a limited capacity for bullshit because I got a job to do here. Okay. Does anyone have lecture? I want to get back to the topic here. Does anyone have lecture notes on Aristotle's argument for a stationary Earth?
I have that he used the model using epicycles.
It's more than that. It's about parallax. He had a powerful argument for why Earth should be the fixed center of the cosmos.
He said there was no observable parallax because of the angular shift in the position of stars due to the motion of Earth.
Okay, thank you. So flush this out with me then. Why does Tycho Brahe charting the positions of stars help resolve whether heliocentrism or geocentrism is the proper model of the solar system?
Did it have anything to do with if the Earth was moving around the sun, there was no observable parallax to the stars?
That's right. Exactly, Ethan. So let's take notes on this because this is kind of a big deal. The big idea behind Tycho Brahe is that Tycho Brahe was hunting for what we would now call stellar parallax. And just to make a quick and dirty definition of it again, stellar parallax would be an angular shift in the position of stars due to the motion of Earth. An angular shift in the position of stars due to the motion of Earth. In other words, Tycho thought that Aristotle's argument was so good and so clear in its logic that all he had to do to prove that the Earth was orbiting the sun was to make really careful observations of the right ascension and declination of a star. And if they changed or shifted over the course of a year, then that would prove that the Earth orbited the sun. And so this was based on Aristotle's argument. You guys can see, and this continued to haunt scientists for hundreds of years to come, that an obsession with the logic of Greeks, an obsession with their way of thinking, is very dangerous because they sound so clever and they're so seductive. They're like Pied Pipers of logic. And they led so many thinkers astray for hundreds of years to come that people eventually found trusting the wisdom of philosophers to be not a good way to go about understanding reality. If you're a scientist, philosophy is very suspect today because of this, okay? Let's write down the two possibilities up here. You guys should have had enough time for those notes. So the idea is if the stars shift, if there's parallax, then heliocentrism would be the correct description of the heavens. If there is no parallax shift, no shift in the angular positions of stars, then geocentrism would be correct. Thank you, Matteo. I think it's time we got rid of him.
Don't disrespect. I'll be back. I'll be back whenever I want to come back. You understand me, sir? I'll be back. And Preston, I'll see you at school tomorrow.
I am not scared of you. Thank you. Okay. Sorry about that, guys. I don't know why. It's like, doesn't anyone have anything better to do? This is hard enough as it is. Okay. So what do you think? Did Tycho Brahe find parallax? Yes or no?
Probably.
No, he didn't. Because he didn't have a telescope. To help you understand why Tycho did not find parallax, let's take the very closest star to our sun. The closest star to our sun is Alpha Centauri, which is 4 light years away, and it has a parallax shift of 0.75 arc seconds. In other words, 3/4 of 1 arc second. How would that compare to the level of resolution that Tycho Brahe had?
Considering the limitations of human vision, he probably wouldn't see it.
No, I want you to be quantitative. Yes, okay, that's correct, Daniel, but be quantitative. What does 3 arc minutes turn into if you convert it to arc seconds? You guys are supposed to know arc minutes and arc seconds, right? What's the conversion factor?
Okay, so if one arc minute is is 60 arc seconds. So that would be 180 arc seconds.
Yeah. So basically, given the fact that the biggest parallax shift that you can discover is less than 1 arc second, that means the star's angular shift was 200 times smaller than what could be observed by the naked eye. So I've created a waiting room so that dorks can't interrupt us. And I don't know, someone's trying to log on named iPad. And I hope that's not an actual student who's trying to join this lecture, but I'm going to say if you don't change the name, I do have a class where someone named John tries to attend, but I don't know if it's this one or my 1020 class. I guess they can watch the video later. I'm just really surprised that I have to deal with garbage like that. Okay, he did not find parallax because he didn't stand a chance. So the largest parallax was 200 times smaller than what you could observe with the human eye. All right, wait, I don't want to say it like that. The human vision, the resolution of human vision, something like that. However, Tycho Brahe did make two observations which I would like to have us write down. And these two observations, even though he should have, and he eventually did agree that geocentrism was the proper description of nature, he did discover two observations that led him to suspect that the Greeks fully understood the heavens. And these are famous. They're now known as the two observations of Tycho Brahe. The first thing that Tycho saw was a comet. And the second thing that he saw is called a nova. And nova is Latin for new star. And I'd like you guys to consider why both of these observations would pose a challenge to the Greek conception of the cosmos. Let's do some slides. I don't know if you've ever seen a comet before, but when you look at a comet, it's something that's easily observable. Well, okay, there are comets that you cannot see with the naked eye, but when a comet comes close to the sun, it's a ball of ice that tends to heat up and sublimate from ice into gas. And the comet is a ball of ice that creates a huge atmosphere of gas around it, which reflects sunlight. And many famous comets, like Halley's Comet, get so bright that they can easily be seen with the naked eye. One of the first comets that I observed as a professor here at CCRI was about 8 years ago now, when Comet Holmes came around. And I had heard that this comet was visible in the nighttime sky. And because it had made the local newspapers, a number of CCRI officials wanted to come and see it at the observatory, which I run on Wednesday nights. And I'm hoping to start those up next week when we go back to class together. Well, I got a little nervous because I hadn't seen the comet yet. And so the first time I was going to look for it was going to be on a Wednesday public open night. And I knew that the vice president was coming to the opening. And so I didn't want to look like an idiot. So I spent all day getting my star charts and getting the position, the rising and the setting time, hoping I was going to find it. So the nightfall is setting and all these people are gathered around, and I'm getting a little jittery because I want to make sure that I can actually find this comet that everyone's come to see. And as soon as it got dark, I just looked up in the sky. I had all the papers in my hand, but I looked up in the sky and I'm like, oh, there it is. I didn't need to do any of that stuff because all you had to do was just look up and then you saw this big fuzzy ball in the sky. It was just that easy, right? So the point I'm trying to make to you is comets, when they're very bright, are not hard to see. Like any person, not just the great astronomer Tycho Brahe, could see a comet. Do I believe that Tycho Brahe was the first human ever to see a comet? No. Why was his observation so important then? I think his observation was so important because Tycho Brahe was probably the first person to realize that thing is not some kind of a goofy cloud or an atmospheric phenomenon. That thing is happening in outer space. And another thing that Tycho Brahe might have understood, if you track the orbits of comets, they are very non-circular. I might have shown this to you in our lecture last time, but if you look at the orbit of Halley's comet, if Tycho Brahe was tracking its position, I think that Tycho Brahe would have understood that the orbit of the comet could not be circular based on the distance that it was traveling in our solar system, how close it gets to the sun, and then how far away from it, the sun it gets. Let's see here. So why is this a challenge to the geocentric model of the universe? Does anyone understand this? The big thing is that the comet would represent a transient phenomena. It's a one-off. It's random, as the kids say. But Plato claimed the heavens were eternal and immutable, and they were not subject to change. So there shouldn't be weird gas balls that come flying in close to the sun. And the fact that its orbit is non-circular would also not be very helpful. The second observation that Tycho saw was a nova, or a new star, meaning that one day, boop, a new dot appears on the sky. And that's what the new star would have looked like to Tycho. And he observed this in 1572. Today, we have powerful telescopes that can observe these coordinates that Tycho Brahe recorded, not only at visible wavelengths, but at X-ray wavelengths, where hot gas seems to radiate. When we look at the same coordinates that Tycho Brahe recorded, this is what we find there today. This is what's known as Tycho's supernova. We have now classified this thing not just as a nova, but a supernova, because he witnessed the death of a high mass star that led to a massive explosion. It created so much light that you could actually see it with the naked eye. So Tycho could not have seen anything like this, but we give him credit with discovery for it. Because he pegged the date of the supernova to 1572, now in 2022, we can study the angular extent to which the gas cloud has expanded, and that teaches us about the velocity and the energy contained within the explosion. It's kind of like we get to study the physics because Tycho Brahe was there to observe it at the beginning. It's a cool collaboration through time that's ongoing between us and Tycho Brahe. So what's Tycho to do? No parallax, suggesting Earth isn't moving, yet clearly the cosmos is more complicated than either of any of the Greeks had imagined. What Tycho did was he invented his own model of the solar system that was neither strictly geocentric nor Copernican. And here's a little description of how it would have worked. First of all, Tycho placed the Earth at the center of the cosmos. And you can see the Earth here, which is just a dot, is at the center of the background sphere of stars, and that accounts for the lack of parallax. Then he has the moon orbiting Earth, and he has the sun orbiting Earth. But check this out. He does not have the other planets orbit Earth. He has the other planets orbit the sun. And this is cool because it preserves Copernicus's description of retrograde motion. In fact, in a modern context, having all the planets orbit the sun, but then having the sun orbit Earth is dynamically almost the same as a Copernican solar system, just with an Earth-based reference frame. although that idea was a little bit ahead of its time. Tycho Brahe's model did not only correctly describe most of the observations of the nighttime sky, but Tycho's positional accuracy was slightly better than either Ptolemy's or Copernicus's. By rights, Tycho Brahe should have had the superior model of the solar system. The truth, however, is that no one liked Tycho Brahe's model because no one liked Tycho Brahe, because everyone thought he was a jerk and a loudmouth and someone who would sword fight people over mathematics. So people were prejudiced against his model of the solar system. All right, so let's make a quick note about this. Tycho Brahe, the last thing we'll say about him is he made a third model of the solar system, which didn't last very long because of what happened next. His model of the solar system had a geocentric Earth, but had planets orbiting the sun. And his model of the solar system had the best positional accuracy. Perhaps Tycho Brahe's model would have caught on over time, but Tycho Brahe died after developing some type of urinary tract infection, and it was because he was getting drunk too much with the king, and I don't know, you couldn't get up to pee during dinner, something like that. I've heard some various descriptions of it. But when he died, his student, his protege, Johannes Kepler, knew that Tycho had the best positional data for the orbits of Mars, and Johannes Kepler stole Tycho Brahe's orbital data for the position of Mars, and he fled to Germany to work on his own model of the solar system. It turns out that his employee, Johannes Kepler, was a secret, devout Copernican believer. And although he would not reveal this to his boss, he believed that the sun should be at the center of the solar system. And he set about trying to make it work. And he eventually succeeded in coming up with the correct description of motion. Now, I'm showing you guys really quickly a picture of something called a Foucault pendulum, which is something I wanted to talk about because I wanted to mention that proving that the Earth is in motion is not a very easy thing to do. People wouldn't discover parallax for hundreds of years after Tycho, well after the creation of telescopes. But the first person who proved conclusively that Earth was in motion was a French scientist named Foucault, who developed an ingenious device known as the Foucault pendulum. And you can find them in science museums all over the world, including the Boston Museum of Science, if any of you have been there for a visit, in the front lobby. Now, the way this works is a little bit tricky to explain, but basically the idea is that a spinning Earth creates rotational forces called Coriolis forces. And in the demonstration, which was originally done at the Arc de Triomphe in Paris, he hung a line with a plumb bob on the end of it, and he carefully pulled it back with a sort of silken cord and used a candle to burn it so that no sideways velocity would be imparted. And he allowed this pendulum to sort of oscillate and swing back and forth from the top of the Arc de Triomphe. And what he did is he encircled the pendulum with all of these wooden pegs. Now let's think about this for a second. If Earth did not spin on its axis, then there would be no reason for the pendulum to change its orientation. And what would happen is the pendulum would swing back and it would knock over one wooden peg, forward and knock over another wooden peg, but it would sort of swing back and forth in the same plane without changing. If you actually perform this experiment, what happens is that over the course of 24 hours, as Earth is spinning, it changes the orientation axis of the pendulum, and it slowly swings through a 360-degree circle and knocks over most of the pegs in the circular orbit. And the only way to explain this is that if Earth spins on its axis, it imparts some sideways forces, some Coriolis forces to the pendulum. My point in just sharing this with you is that is a very ingenious and not easy thing to think up. And it's not easy to explain unless you know some serious physics. So my point is, these folks who were investigating the nature of the universe had a very difficult job ahead of them to prove that Earth was actually in motion. It's a funny thing to think about since we take it for granted today. Let's take some notes on Johannes Kepler. Here's where we're going to get into the real work of the day. And hopefully I'll have enough time, I think I do, to develop the the Keplerian model of the solar system, okay? So note-taking time. Johannes Kepler was a German mathematician, also an astronomer. He was sort of the, I don't know if we should say student, maybe we could just say in modern day terms, he was sort of graduate student to Tycho Brahe. Although I'm sure they didn't call it a graduate student in those days. And he was a secret believer in the Copernican solar system. Because he had helped Tycho Brahe take observational data for the position of Mars, he knew that Tycho Brahe had the very best astronomical data. And upon Tycho's death, he stole the orbital data for the positions of Mars and went to work on a heliocentric model that would describe the positions of planets better than Tycho's model, better than the Copernican model, and better than the Ptolemaic model. And he found that he could do it. It only worked if he got rid of circular orbits. So let's cross out circular orbits. If he replaced the orbits of planets with something called ellipses. And an ellipse, for the time being, is sort of a squishy circle. Ellipses are going to be what we focus on during our lab today. And I'll show you a quick model of how we're going to do that. There is a technical mathematical description of an ellipse, but it's ugly and it uses trigonometry. What we're going to do to make one today is we're going to take that cardboard that I talked about at the beginning of lecture. We're going to take two thumbtacks and we're going to put them into the cardboard. And we're going to tie a loop of string around the metal part of the thumbtacks or push pins. Then you take a pencil, you put it through the string and you drag it along the paper, and out comes an ellipse. And the technical requirement for an ellipse is that the perimeter of this triangle between the two focus points and any point on the ellipse, the perimeter of that triangle must remain constant. So that's the difference between any squishy old oval and an ellipse, is that that perimeter must stay constant. And so it's quite easy to make one with some cardboard and some thumbtacks and a loop of string. That's what we're going to do today. Although we're going to make a perfect geometrical ellipse, I think we might start today with a quick model in our notebooks, because you have to know these things for your exam. And I need to use some of these terms to describe how Kepler modified the orbits of planets. So I would like to erase this with everyone's permission. Object now if you have one.
Oh, I just need the last bullet.
That's fine. Take that. I'll see if I can rustle up some iced tea. Hold on.
Okay.
I don't care. I just need liquids. My lovely assistant is going to help me with some iced tea.
I have a little question. So for
Yeah.
next week, we have class in person.
I guess so, right? Isn't that what's happening?
Yes. On
Who's
Monday.
talking to me right now?
Me, Mateo.
Oh, hi, Mateo. What's up?
No, I was just wondering that we're gonna just shift to in person.
I guess, yeah, to be honest, I guess I should have double checked, but I believe the plan is for classes to resume on February 14th, which is Valentine's Day, right?
Yeah. I also like, would you record the sessions?
Yeah, it turns out that this model kind of works pretty well, doesn't it, Mateo?
Yes.
Yeah, people like this once they get used to it, don't they?
Yes.
Mateo, the short answer is I'm going to try, but what I discovered, thank you very much, when I try to do this before, is that weirdly, these recordings perversely work really well at my house because I've got this like perfect little board that fills up the screen. I tried to go back, when I went back in person last semester, I thought, wow, this was such a great experience. It's so useful to have these recordings. Why don't I record every lecture? So I tried doing that with the little cameras that they have, and it didn't work. It didn't work because right now I'm talking to you and I'm focusing on all of you through the screen. But once I'm in class, I'm kind of looking around the room at the people in class, and it was hard to kind of stay engaged and focus with the camera. The second thing was that I was taking notes on a much larger whiteboard, and it was hard to capture the notes on the whiteboard and me and what I was doing. You know what I mean? It became difficult. I would actually need like a professional TV studio to make it good. Now, with that being a caveat, Mateo, I might be willing to try again, maybe setting up my laptop and trying to record it, but it just doesn't work the same. I do have lectures from a previous semester we can use, but I think if you signed up for the live class, you might have to come in live at some point, especially for tests, right?
Yes. Okay.
I'm not unsympathetic to what you're saying. To be honest, this model works great for me, and I would like to keep doing it this way too. But I take my responsibility as a professor serious. So when
I was just like wondering because like, what if I have to like miss a class?
Then we'll probably use one of the older recordings, but they may not sync up exactly the way our class does. There are ways around that, and we'll deal with that when we get to it. But I am willing to try, Mateo. I just can't guarantee it's going to come out good because it didn't last time. Does that make sense? Cole, what are you thinking?
What classroom will we be in?
Oh, great question. I actually was just thinking about that I probably want to get it changed because let's see if I'm logged in here.
I should also mention, because my student email keeps haranguing me with this, that if you have to go on campus, you have to make sure that you've got a booster. You're gonna need a special sticker on your ID again.
Right. I do have a booster, and I think I uploaded that, so I should be okay. But that's a great point, Daniel. People might not be thinking about those things, so I appreciate that contribution. It looks to me like we're scheduled perfect. This is a good room. So we're going to night 6062, okay? That's one of the big classrooms on the 6th floor. Our lab room is 2050, and I'll tell you about that. That's on the 2nd floor, but 6062 will be our lecture room. We'll also be going, Ethan.
And are we still gonna do like Mondays going to do lab and then Wednesday homework?
I think that's going to start getting tricky. I would love to do that, but I think there's going to be too many of us to fit in the lab room. So I think what's going to happen is we're going to have to do, this is going to suck a little bit, guys. In fact, we should have talked about this. When we all go back in person, your class is too big for everyone to do lab on the same day because of the restrictions of the lab room. So we're probably going to have to do Monday lab, Monday people come to lab, and then we'll try to do the homework after. And then Wednesday people will do the lab and do the homework after. That is going to suck. It's going to be a longer session than we have right now. That's one of the reasons I particularly love this model. I used to be able to do this model when I had student tutor helpers, and I haven't had those for a while. I don't know. I've got to figure some stuff out. You know what? This is starting to make me realize that I've got some things to think about. So I at least know what classroom we're going to be in, and I know how this works, but it's going to be a little rough, okay?
What floor did you say the 6062 room was?
6th floor. Since it begins with a 6,000, it's on the 6th floor, okay? Have you guys all been to the Warwick campus before? Are you familiar with it? Oh, it's a little bit of a maze, Marissa, but it's kind of a cool building. It looks like a giant spaceship, okay? You'll love it. It'll be exciting, I think. Or try to love it because you've got to do it. Okay, wait, we're almost, I think we're getting out of time here. It's 12:40. Let me finish this lectures on Kepler's laws before we go forward, okay? I hope that person got their last bullet point because I'm going to erase now.
Yeah, I did. Thank you.
Okay, let's make a quick and dirty model of an ellipse. So actually, no. We're going to do an ellipse. We're going to do an ellipse in just a minute. I don't want to repeat myself twice. Let's do Kepler's 3 laws of planetary motion. So Kepler wrote a book. And Kepler's book was called Harmonices Mundi, on the harmony of the worlds or something like that. And in it, he put forward what are called his 3 laws of planetary motion. And this is a pretty big deal in astronomy. You can definitely expect to get tested on these laws, because this is the first time that anyone ever got something really right in astronomy. Like they actually figured out how a thing worked, and it was a successful description of nature. Modern astronomers continue to use Kepler's laws because of their usefulness. And the laws go something like this. First, the law of ellipses. The law of ellipses states a planet orbits the sun on an ellipse with the sun at a focus point. So circles are out, ellipses are in, but the sun is actually not at the center of the ellipse the way Copernicus might have imagined it, but instead the sun would be located here at one of the focus points. That means that during your orbit, there's a closest approach to the sun. We know that vocabulary term. It's called perihelion. And there's a farthest distance from the sun called aphelion. Let's take a look at how the planet orbits the sun. So we can see here, this would be a sort of model of a planetary orbit. And ellipses have a number of parameters that we're going to be labeling. They have a distance from the center to the focus. I call that the focus offset in blue. They also have something called the semi-major axis. It's the distance from the center to the edge, or half of the major axis. These 2 parameters help define something called the eccentricity of the ellipse. The eccentricity of the ellipse, which you get by dividing, in our lab today, we're not going to call this C, we're going to call it X, okay? X is going to be the focus offset. I like to reserve C for the center of the ellipse. The eccentricity is kind of like the percent squishiness of your ellipse. E is a number that can be equal to 0 and go all the way, but not equal to 1. So its domain is anywhere from 0 to 0.999 forever. And that means it's a percentage, and the eccentricity shows you the percent squishiness of the ellipse. And if I could, just as a quick digression here, if I type in eccentricity and I go to images, this animated graphic here, this animation, gives you a little sense of what different eccentricities look like, right? You can have an eccentricity of 0, which is actually a perfect circle. So a circle is actually a special type of an ellipse. But then as the eccentricity goes to 0.5, it gets more egg-shaped. And by the time you get up to 0.95, it gets kind of cigar-shaped, okay? So it's just telling you how squashed your planetary orbit is. The second law of Kepler is called the law of areas. And it tells us something about how a planet travels around the sun with time. One of the dictums of Plato regarding the heavens is that planets had to travel across the sky with perfectly uniform motion, meaning traveling the same number of degrees per day across the sky. And that turned out to obviously not be true. You can see that even with retrograde motion. Kepler discovered that the planets sometimes move very fast when they're close to the sun, and they move very slow when they're farthest from the sun. But that if he created a line that connected the planet to the sun, and he measured the area of the little triangle that they swept out, that the area in this short skinny triangle would be equal to the area of this short squat triangle, so that if the planet traveled from A to B within 2 months, but then later on in a 2-month period traveled from H to I, you can see that the distance traveled in 2 months is not the same when it's close to the sun versus far from the sun. Even though the distance is not the same with time, the area that the planet sweeps out should be constant. And the area of this short squat triangle is magically always equal to the area of this long skinny triangle, as long as the time is constant. So the simple way to say that is a planet sweeps out equal units of area in equal intervals of time. The third law is what was referred to as his harmonic law. And here Kepler found a mathematical relationship. You had to use it in your homework last week, so you should be slightly familiar with it. The relationship is that p squared is equal to a cubed, where p is the sidereal period. And let's make sure we write down sidereal because it could be confusing on a test. It's the sidereal period of the planet, measured always in years. And A is what we might call either the semi-major axis or the average distance between sun and planet. And that needs to be measured in astronomical units. These three laws correctly describe the motions of planets around our sun. And that's why they've been useful to us even up to modern day times. Okay, I think I've used up my time for a lecture for the day. There's a few more things I could say about this, but maybe I'll pick up here next time. What we're going to do for our lab today is we're actually going to make a model of an ellipse. Now, I wanted to put this into your notes, but I'm realizing that since your labs are probably being done in your notebook, because all you have to do is take a picture and send it to me right now, because of that, I can probably just have you do the real ellipse, and that can be the ellipse that's in your notebook. Is that what you guys have been doing up to now? Up to now, I'd imagine that if I was a student, I'd be doing my homeworks in my labs kind of in my notebook and just taking a picture. Is that what you have done? Yes or no?
No, for the labs, you told us to print some papers and then we do them and then we.
That was one way to do it. Yeah.
Yeah. But my homeworks I did in my notebook in
Right.
my.
When we go back in person, of course, that will change. You'll actually have to turn in a physical lab and I'll print them out for you and turn in a physical homework. You'll write them down on. Make sure you have some paper that you can tear out or one of those notepads where you can, rip paper off. But today, Mateo, that's fine if that's how you've been doing it. No biggie. But today you could do your lab in your notebooks if you want it. Well, actually, no, I still say you print them out. I'll tell you what, Mateo, at the beginning of next class, I will do a model of an ellipse for your notebooks. If you do have printer paper, and I'm a little, oh, I printed mine out. If you do have printer paper, then go ahead and print this out because then the focus points will be at the right distance and stuff. That's fine. If not, you can do it in your notebooks. Okay, that's great, Daniel. Do we like our little 10-minute break before we do lab? Is that helpful to everyone? That lets me have some tea and stuff, right?
Sure.
Yes.
Okay, so let's see. What is it iPhone time? It's 12:58. What do you say? You choose 1:10 or 1:15. When do you want to start?
1:15.
I like that too. Is everyone in agreement with Nina? Is that acceptable? All right. We begin at 1:15. I'll see you then.
Is the recording stop?
Oh, sorry. Do we want to not have this on recording?
Yeah.
Class, welcome to lab number 4. We are going to make a model of an ellipse, a model of a planetary orbit in our solar system. To do today's lab, we're going to need the following things if we want to do it correctly. We, of course, need the single-page printout from our planetary orbits lab. And we just need page 5-5, which has 2 focus points. Now, I want to mention that the 2 focus points are about 12 centimeters apart. So if you're reproducing this on your page, you want to do them about 12 centimeters apart. We're also going to need a loop of string. And this loop of string here is a little, it has to be greater than 12 centimeters. So I think this one, let's get this in the back of a white piece or in the back of the cardboard. This string, once tied into a loop, is roughly a little over 15 centimeters, if you can see that here. And that's gonna,
do you think a shoelace will work, or is that too big?
the reason why a shoelace might be too big is we have to go underneath the thumbtacks, right? And I think the shoelace might be too thick. A ball of twine, maybe some dental floss, if it's thin dental floss. Whatever you got, Daniel, looks good. Here's the deal, Ethan. If you can't find cardboard, string, thumbtacks, and such, you might be able to do this lab using my pre-made drawing of an ellipse. Now, this is pretty cheesy because the whole purpose of the freaking lab is to make your own ellipse. But I understand that things are complex. This is another reason why going back is kind of nice. So you'll see here in this thing, I actually drew out the ellipse for you. So if you want, you can print that and use that in its place.
Oh, that's the one that I printed out anyway. Was I not supposed to do it? I have everything. Like I have everything. I have the cardboard and the 2 thumbtacks.
I would say then, if you don't mind, keep that printout handy in case you fail. But why don't you try to print out quickly 5-5 and do it right? Because I think that's the whole point of the lab, is to do something with your hands, to mechanically see how the lab is done. This lab, guys, does not take long. It's like a half an hour, 40 minutes tops. It's wicked easy. And it's just about getting your hands dirty with ellipses because we have to understand them, right? So Ethan, hit print on that thing if you can. It's probably—
Yeah, where do I
what you do is you go to
I'm looking at your screen.
Hold on. You go to Blackboard and open up LAB4 planetary orbits, right? And then hit print and just print page 5. That page 5 is what you need.
Okay.
Does that make sense?
Yeah.
Okay.
Give me 1 minute.
But you guys can use my pre-made drawing of an ellipse if you're not capable, okay? Okay, let's switch over to my remote phone so that we can kind of make this ellipse together. Hopefully this will work correctly. And it looks like it is. Now, it's very important, class, that you continue to label your name and your section and what lab this is. I've had to cuss a few people out on this. People aren't labeling their labs, and it's causing great confusion. So please do not be one of those people. Sorry, what did I do? Here's my. Okay, so usual business here. Hopefully no one joins the waiting room. Okay, yeah, I have to do a waiting room now because of those losers. Okay, so put your name at the top, okay? Write onto it lab number 4 so that I know and you know what lab this is. And then put AS1010. And it's very important you know what your section is. You're either in 001 or 002. 1 is the Wednesday lab, 002 is the, sorry, 001 is the Monday day lab, 002 is the Wednesday day lab, and the night class only meets once a week. They're 101, I believe, okay? And they meet on Monday nights. And since we'll be going back next Monday, if you're in the night class and you're watching this video, be aware that I'll send you an email, but we will be meeting for the Monday night class. Mondays, we'll actually meet at 4 p.m. to do office hours before class. And the office hour room is right next to my office. It's gosh, what is it? My office is 2030. It's 2201. And I'll probably send out an email with instructions on that. Well, anyways, look for an email with that information for faculty, just for the night students who are watching this later, guys. Faculty detailed day and time. Come on. The Monday night class, it has us meeting in night 6404, but I'm going to see if I can get that changed. I need to send that email out later. So I'll send that stuff out right away. Oh, shoot. I forgot that I was sharing to my iPhone. I should not have messed that up. Sorry. Okay. All right. Here's what we're going to do. We're going to take our piece of cardboard and we're going to place our paper over the top of it. And I'm sorry that I can't really do this sideways view. So I'm just going to go sideways for a second so you can see what's going on. I'm going to take 2 thumbtacks and I'm going to place them at the 2 focus points. So I'll place them vertical, sort of punch them really down into the cardboard. You might even want to put your cardboard on top of something to do this right. And I'm going to place the loop of string underneath around the metal part of the thumbtacks. Push these down in deep or put some padding underneath. Then I'm going to take my pencil and I'm going to hold it tight against the string. And I'm going to drag it around to make a perfectly formed ellipse. And when I'm done, I will remove the cardboard from underneath. And that way I'm not writing on top of the cardboard. This should be kind of what our model of an ellipse looks like, okay? Did you guys see how I did that? Why don't you take a second to do that?
I am sorry, but I'm not artistic nor good with these things at all.
Well,
You wouldn't be
but
the
that's
only
sort of
one.
the thing is we're practicing and we're learning. So see what you can do. If not, you've got my model of an ellipse, but
I was gonna say that it's not there.
Okay. So, question. So for the pencil, where exactly would I place it on here? I know it's upside down, but
you push it against the string, keep it tight. So the way I did it, let me reproduce this again. Thumbtacks in, string around the paper, around the push pins, right? And then you push the pencil and keep it tight so that you make a nice triangle and you keep it tight against the string. And then you sort of drag it around with the pencil stuck into the string. Sorry, there's a little lag or a little delay here, right? Why don't I see what I'm working with? Can someone hold up and show me their ellipses? Anyone? I don't want to go forward until I feel like you guys are ready.
Wait, 1 second, 1 second.
Maybe I should pause the recording until you guys have this figured out. Can I do that? How do I do that from? Pause recording. Okay, now that hopefully people have some sort of an ellipse going, we are going to make a model of a planetary orbit. And in our model of the solar system, 1 centimeter on the page is going to be equal to 1 astronomical unit. And I want the precision of our measurements, the tolerance, to be plus or minus 1/10 of a centimeter. So in other words, when I say 1/10 of a centimeter, that means we are going to take measurements to the nearest little black tick mark, the little millimeter tick mark. If something ends up at 2 centimeters, if it's not 1.9 and it's not 2.1, you have to say 2.0 to show me that you're at the 1/10 of a centimeter precision, right? First thing we're going to do is we're going to draw in our major axis. And let me see if I can zoom out a bit here. I thought I could zoom. I could zoom in, so I can't zoom out. I'm going to go sideways so that you can see me with the camera. So what you see me doing is you see me connecting the 2 focus points with my ruler. Okay. Actually, here, let me go perfectly sideways here. And I'm connecting those 2 focus points, and I'm going to draw in the major axis. I'm going to go edge to edge of the ellipse, but not farther. 2 points make a line in Euclidean geometry. I'm going to make sure I don't have any hangnails there, okay? This is my major axis, and I'm going to measure it. And you guys are going to watch me measure this here. I'm going to put 0 at one edge. And I'll carefully line it up against the ruler. I hope this is the good one. I have 2 rulers here. This one looks a little better. So I'm going to line 0 up with the edge. I'm going to take my measurement. You'll notice it's at the 17.8 tick mark, right? This is 17.5, 17.8. The line is clearly stopping before 17.9. So down here for my major axis, I'm going to do 17.8. And since it's a model of a planetary orbit, I'm going to say AU, not centimeters. Now, I'm going to take this number and I'm going to divide it by 2. Have your calculators handy here. 17.8 divided by 2. 8.9 is the midpoint of my ellipse. So I'm going to make a dot at 8.9. And this is going to be the center of my ellipse, C. And once I have the midpoint, I can draw in my minor axis. I want to make sure it's perfectly perpendicular to the major axis, like so. Here. Okay, so here you can watch me carefully draw in my minor axis. Make sure it's perpendicular to my major axis, okay? And now I can label this as the major axis. Should do everything that I do here. And we're going to label here the minor axis. So the major is the long football axis. The minor axis is the short one. Let me clean up my ellipse. Let's choose one of our focus points to be the sun, because that's how Kepler's laws go. So actually, I'm going to do this kind of nice. I'm going to use a little circle maker here. These are kind of nice to have. And I'm going to center it on the focus point. And I'm drawing a little circle here to represent the sun. I'm going to label it sun. And maybe just for fun, I'll even put some beams of fire. Sorry, some beams of light coming off of it. The sun is not a ball of fire. Okay. Now, if the sun is at the focus point, the planet is on the ellipse. So I'm going to go to some random part of the ellipse. And I'll put a little planet like Jupiter or something on it. I'll label that as planet. And I'll demonstrate that the planet is orbiting counterclockwise around the sun as seen from north. Once I have the sun chosen, I can now identify this point. This is the closest approach to the sun in orbit. That is perihelion. That's the perihelion point. And over here, farthest from the sun, that's the aphelion point. So I'll label that as well. So I've got my sun, my planet, center, focus points. I've got perihelion here, and I've got aphelion over there. I now want to label two other parameters, X and A. Let me put this in my tape holder here. X is going to go from the center to the center of the sun. So this is X right there. But A, the semi-major axis, is going to go from the center all the way to perihelion. So A is the semi-major axis. It's half of the major axis, whereas X is the distance from the center to the focus point. So X is what we call the focus offset, and A is what we call the semi-major axis. We can write that in as well. Now, our first job here is we have to measure perihelion and aphelion. To measure perihelion means how far from the center of the sun will perihelion be. So I'll take out my ruler. I'll put 0 at the center of the sun. And if I look close, it's at the 3 centimeter line. But I want to demonstrate that it's not 2.9 and it's definitely not 3.1. So to show that I have 1/10 of a centimeter precision, that I actually looked to the nearest little tick mark, I will label my perihelion as 3.0 centimeters. That means I took the time to measure to the nearest little tick mark. Now I measure the aphelion distance, which
You're moving too fast. Could you go back again?
sure. Tell me what you need from me.
So I put the X as focus offset and then A. I can't see that well.
Can you see now?
And my major axis. And how did you measure the 3 centimeters for the perihelion again?
Well, excuse me.
Well, it's going to be different. But
Yeah.
put it for the sun. Okay.
Your measurements may be different unless you're using my ellipse. I measured from the center of the sun to the perihelion point, just like that.
And you're using 2 sig figs?
Yeah, in other words, I can see that the line is at 3.0. It's not at 2.9 and it's not at 3.1. Can you see that?
Yeah.
So if yours ends up right in that line, fine, but you're supposed to take your measurement however it is, you know?
Okay. Yeah, that's fine. Okay, now I get it. Okay. I'm okay now.
Sure, just keep me in line, Matteo, if I go too quick. I hate going too slow, but I might take it too far sometimes. Let's do aphelion. That's from aphelion to the center of the sun. So just to show that you guys are with me, here you can see I've got 0. What would you say is the aphelion measurement here?
3 centimeters?
No.
From where? Oh.
From aphelion to the sun, which we marked over here.
Oh, 15 centimeters.
No, that's being sloppy. I want 1/10 of a centimeter precision.
I can't see that. Okay, 14.8 or 9.
It looks like
Centimeter.
14.9 to me. It's 1 tick mark
Okay.
before. Now we have to measure X. X goes from center to the focus point. What do you think?
5.9 centimeters.
Oh, shit. I guess I should stay consistent here. If 1 centimeter is equal to 1 AU,
Oh, okay.
to make it more planet-like, I'm going to make it AU. Sorry. I was mixing and matching there. Okay. Now we're going to do A, semi-major axis. What do we think?
Where do you measure that from?
Well, look at your label. A goes from the center to the perihelion. That's what we labeled it as underneath there, right?
Yeah. So 8.9 AU.
Next up, we're going to calculate what's called the eccentricity, the percent squishiness. Now, down here, let me see if I can, maybe I'll do it over here. I just need to hold this. The formula for eccentricity is that E is equal to X over A. So my E is 5.9 AU divided by my A, 8.9 AU. AUs are going to cancel out. This is an important part of eccentricities. They're unitless. They have no units because they're just a percentage. So let's type in 5.9 divided by 8.9. How many sig figs do you think I should keep?
2.
That's right, because we have 2 top and bottom. So what should I round it to then?
0.66.
Very good. 0. Always put your leading 0 out front. This matters to me. So leading 0 out front, 0.66, no units. That's the kind of thing I should see.
Do you mind just going over how you got A one more time? I missed that step.
Sure. Did you diagram A in your diagram? Of
Yeah, I did.
Then
Yes.
you can see from your diagram, that's the point, is that A starts at the center and goes all the way to perihelion, right?
Oh, okay.
So I measured with a ruler from there
Yeah,
to there.
no problem.
But that's fine, Ethan. I don't want explaining it again. Okay, now that we have our eccentricity, we're going to go for the period P. And do you guys remember the formula that lets us do this? What formula should I use? If I know the semi-major axis, how do I get the period?
So period equals the square root of 8 cubed.
P squared is equal to A cubed. That's Kepler's harmonic law. First, let's square root both sides. P is the square root of A cubed. Now I've measured A as 8.9 AU. And I want you to do the work on your margins, just like I'm doing. P is equal to the square root of 8.9 cubed. So what I will do is I will take my calculator. I will do 8.9. Now the cube key is in orange right there. So I have to hit Shift cube. And that is A cubed. But now that I've cubed A, I've got to deal with the square root. So with that number still there, I'm going to hit Shift square root. Oops. What should I round to? How many sig figs?
2.
2. So what should my final answer be?
26. 27.
Yeah, because if you round up 0.5, that's 27. And what should the units be? Look at your notes to figure out the units of P.
Years.
That's right. It always comes out years. YRS. And that, my friends, is what I wanted us to do for Lab 4. I should see all of that stuff on your lab that you turn in, or I might be tempted to deduct points.
Okay.
Easy
And I'm
enough?
taking notes of that way I get my ellipse right.
Say that again, Daniel.
I'm also taking notes of that way I get my ellipse right.
Yeah, and we'll do this. We can put this in your notebooks next time so you have it in your notebooks as well. Hold on, let me leave this mode. Everyone's got a good look at that now. Let me leave iPhone mode. And let's go to gallery. So hold that up again. I might be able to see it a little better this time.
Yeah, I'm gonna put a flashlight aim at it so you can see it better.
Sometimes too much light is a bad thing. Just hold it up first.
Because I just didn't have enough. Maybe this will make it worse. Maybe it'll make it better.
Yeah, you're already too bright. No, keep it right there. Oh yeah. That looks great, Ethan. I like everything I'm seeing there. That's awesome. So you did a good job. Mateo.
Let me just show you this.
Yeah, that's
I know, like, drawing is horrible, but like, I'm sorry, but
had we been in lab, I might have made you fix it up, but seeing as you're doing it by yourself at home, I'll accept it. That's fine. How about Marissa, Daniel, Cole? What's up with you guys? Marissa looks good. Cole, it's fuzzy, but I think you've got all the elements there from what I can tell. And Daniel, are you okay?
Mine's a work in progress, but once I get the ellipse in, it will look a little bit better.
Okay, Nina, hi. Do you want to show me, Nina? There you are. You're hiding in the troll verse, but you were working with us, Nina, and I like it. I think you've got it. Hold on, hold
Can
it
you
up.
see it?
Yeah, but hold it steady for me, buddy.
Okay.
Hold on. Let me go to speaker view and let me click on your thing here. I see XA, yeah. And your measurements came out the same as mine. Were you actually measuring them? Because your ellipse looks.
Yeah, I had my ruler. Yeah.
Okay, all right, fine. Well, then we're cool. Just upload that and I like it, okay? So everyone, I feel like you're doing pretty good, okay? So listen, I'm gonna end the class in a moment, unless you have any questions, but the takeaways from today are we're doing lab 4, the ellipse lab we just did. On Wednesday, we will meet for our final live Zoom session. We'll do 1.5 hours lecture, then we'll do our homework number 4, which is pretty tough, actually. Hopefully I can get far enough along in the lecture to get there. And then we will meet in person starting Monday, February 14th. All right. All right, guys, be in touch if you have any questions and I will catch up with you soon. Okay. I'll grade some papers today too. Peace out.